Superstorm Sandy, Rama Krishnagiri.
Close enough. Rama Krishnagiri, yes.
Krishnagiri, I'm sorry. Stephen Esposito.
We will discuss the effects of Superstorm Sandy. We're going to split the presentation, Steve and I. New Jersey DOT, of course, is the owner of the bridge. In this picture here, the lower structure is the Mathis Bridge. It's a double-leaf bascule bridge with 66 spans, approach spans. And the bridge on the top is the Tunney Bridge. Mathis Bridge carries the eastbound traffic in from the mainland, and Tunney Bridge takes the shore traffic away to the mainland, westbound. Mathis Bridge was constructed about 65 years ago. It's about 4,900 feet long, and the 66 simply supported spans are multi-stringers and supported on hammerhead type reinforced concrete piers with untreated timber piles. Whereas the Tunney Bridge is the high-level adjacent parallel structure, similar length but less number of spans, longer spans, and also founded on treated timber piles and steel piles. It's built about 20 years after the Mathis, therefore, is less deteriorated condition. As we speak, a major rehabilitation of the Mathis Bridge is being completed, where we replaced the entire decking and the bearings, about 600 odd bearings, 180,000 square feet of precast decking. We did a major mechanical, electrical rehab, safety improvements, new gates, and all the related safety work. And during design in August 2012, just about we were complete with the design, and as part of the design we had a in-depth underwater inspection done because we were addressing some localized scour areas on the bridge piers on the eastern part of the bridge. And our underwater inspection sub had just about completed all their work, and they used this extensive soundings via sonar technology, and they did a very detailed bay bottom survey because we needed that to deal with the permitting agencies because of the amount of fill that we were going to place or whatnot. And at that time, other than what scour was noted before, nothing else was uncovered. Everything seemed to be consistent with what we have been seeing over the years. Well, here's the aftermath of Sandy. For folks that recall, New Jersey took the hardest hit. Landfall was made October 29th. I recall distinctly, it was a Saturday. Our structural folks had inspected the bridge on the Thursday before. We had wrapped things up. And there was still some uncertainty as to where the storm was going to make landfall. Well, Saturday morning it did in New Jersey. And this picture is courtesy of the New Jersey DOT. John Longworth, who is the manager of operations and maintenance engineering, gave us a bunch of these pictures that he was able to take when they were allowed to even go there. We are looking now in this picture towards the west. The Mathis Bridge is on the left and Tunney Bridge is on the right-hand side. So clearly you see what happened there. And further east, it was a nightmare. There was no in or out of that Seaside Heights, the town that got hit the hardest. And even the DOT wasn't even allowed to go there. Everything was shut off immediately. For about good 2 weeks, nobody could access the barrier islands. Nobody could go in, nobody could get out, even emergency personnel. There were police stationed throughout, and the first chance that the NJ DOT got to go back out there was mid-November or so. And this is another picture that we got from Jack Longworth, just to show that everything was pretty much a ghost town at that point. Well, from the field, Jack called and said, well, you know, from what I'm seeing here, there's not much that we can determine. Yes, it seems like the bridge is still looks stable, but we don't know what's going on underneath. So we got to get a diving inspection done right away. And we had a diving inspection scheduled through the structural evaluation folks who pretty much manage all the bridges in New Jersey. There was one coming up in January of that year. Well, we pulled that back to November because we wanted to see what was going on underneath. And without getting into each one of these slides, I'm going to try and spend time on one or two so you get the picture as to what the divers uncovered. On a daily basis, because it's a 66-span viaduct, they could only dive so much each day. We were getting information on a daily basis, sharing it with the NJDOT, coming up with options for immediate repairs. The reason being that, here's one slide that I'd like to stop for a minute or two. In this picture here, the lowermost line is where the divers sounding uncovered what was going on. The top dashed line is what we call the baseline soundings, or what was recorded earlier on, the first time ever, and it closely matched how the bridge was built 60 years ago. Over the years, there's been a little bit of fluctuation, as it does occur with any tidal waterways. Material gets deposited inland, inbound, material gets taken out. So up to a foot or 2 feet of fluctuation in the bed, we don't really get too concerned. But when you see 13, 14, 15 feet of scour, it's time to do something. And that's about what we found here. As you could see, the general trend was a significant lowering of the bed, and for whatever reason, the storm flow favored the easterly 20 spans of this viaduct. And I'm only showing you about 4 or 5 spans here. At the worst location, which was, let's say, piers 11, 12, and 13, from the bascule span out, the divers found about 13 feet of scour, or overall 15 feet of scour, and 13 to 12 to 13 feet of exposed timber piles. And that's what you're looking at here. I gotta tell you, there's the picture, the sketch with the deepest scour is a bit misleading because there's a break line in the piles that you don't see. The piles really do go down about 50 feet below the pile cap, and we had lost at about 12 feet of that embedment at that point. And like I said, this information was coming in on a daily basis from the field. A couple more shots. The divers could practically swim from one side to the other. The piles were on 3 feet centers, 12-inch timber piles. At this point, the bridge was still close to traffic. Now, fortunately, we had all the data on hand, all the previous underwater inspections from the 90s, as-built bridge plans, the length of the timber piles based on the as-builts. So the first task we needed to do was, can the bridge be reopened? Because what had also happened is when Sandy hit, the detour routes for this bridge also got significantly affected. So much so that the Manteloking Bridge, which is north of the Mathis, was closed off for a longer term because the approach roadway was completely washed out. So we couldn't put traffic on that route. The other option of putting traffic on Route 35, which runs north-south, was also not viable because that road itself was damaged. So as you could see, the DOT was under the gun to get this bridge open because emergency access into the island, barrier islands, and getting the devastated material out was really, this was the only 2 twin structures that could accommodate that. So Thursday, I recall, all the information came in, and Monday they had to have a decision on what happens. Can this bridge be opened, or does it need to be closed off for a long duration? Well, we mobilized immediately. We had about 13 folks at one time working on this, geotechnical, hydraulics, structural. And they looked at all the data that we gathered or was submitted and looked at the critical pier from the geotechnical aspect, a single pile capacity versus a group analysis for deflections, because about 25% of the pile embedment at that point was lost. Fortunately, the analysis showed that the remaining embedment could still sustain at that point emergency vehicles, because we ran the numbers for HS20, and that umbrella pretty much included emergency responders to and back from the islands. Then the next task became informing the DOT. Friday, 2 o'clock, we told them, yes, we feel comfortable in saying that you could reopen these 2 bridges come Monday, which was a big relief for all. And at the same time, we mobilized another team of structural engineers as well as other disciplines to go out there and look at the physical conditions that the divers couldn't see, obviously, because the bearing levels had to be looked at, the plumbness of the piers had to be looked at, plus any damage on the deck itself, which we did. And the Coast Guard, we had to get special permission to access the site because everything was closed off, obviously. And the DOT stepped in again and got us the special permission, so we mobilized the team. And this just shows a picture of the top of the bridge post the Sandy, where you don't see any kinks or dips in the roadway. So that was a good sign that nothing had rotated out of place. Fortunately, too, the piles that were exposed only for about 2.5 months at the time, because being that they were enclosed in the dirt or sand for all that time, they were preserved intact. The divers couldn't poke any more than 1/4 of an inch with the awl. So all these things worked in our favor in getting the bridge opened up to traffic without doing any emergency repairs at that point. The next step was that we met at its office, and Steve's going to discuss the design and scour countermeasures that we placed there, and more so how it has performed over the last few years, which is also an important aspect of this presentation. With this, I turn the presentation over to Steve.
Really, once the immediate need to open a bridge to emergency vehicles was completed, we started looking at how to restore long-term stability to the structure. So several options were considered, including what was submitted with the underwater diving emergency repairs that were recommended. First and foremost, we looked at riprap, which is pretty common and pretty easily to install. However, DOT really wanted something that was going to provide that long-term assurance, and NGDOT doesn't really consider riprap to be a permanent countermeasure at their structures, and also the hydraulic engineering circular takes a similar stance. So that one was kind of ruled out early in the process. After that, we were looking at some of the sheeting options that were presented, either timber or steel, basically putting a perimeter around the piles. But that raised some concern as well, especially for the headroom that was available. If you see in the picture on the left-hand side, the lower level structure is the Mathis Bridge, and you only had maybe like 3 or 4 feet between bottom of structure and top of water in some locations. So that was going to be difficult. And there was also battered piles on the outside perimeter of the foundation. So the overall footprint of that sheeting would have had to be very large to accommodate the geometry. So that was considered not a good option as well. So we started looking at other ways to first and foremost fill the void. So we saw there were options to either place pre-grouted sandbags in the voids, or also placing Fabriform bags underwater and then filling them with grout in place. So we were considering that as a good way to fill the void, but we wanted to provide some long-term stability as well, so that the DOT wouldn't have to worry about this structure the next time a storm came through. So essentially we looked at providing these grout bags as strictly a fill material, but then lining the perimeter of these grout bags with some form of scour countermeasure. And we ultimately selected Ajax armoring units for this. So there's a couple of slides on what Ajax are if anybody's not familiar, but they're precast armoring systems that interlock to each other to provide a large mass to resist the forces from the storms, and it helps kind of dissipate the velocities of the surge as well. So some of the things that we were considering throughout were making sure we were going to have a repetitious construction method that could be achieved, The materials would be readily available because this is an immediate need, and the overall constructability. These are a few photos of the grout bags. This is not our project. This is from somewhere else when we were doing some of our evaluation. But we had a little bit of a unique case where we had a rather high wall that we were going to build with these grout bags. As Rama mentioned, anywhere between 15 feet of scour depth and 12 to 13 feet of exposed piles that were going to need to be filled. So this is one of our details that we included in the contract documents. This is really for the areas with the most scour. So what we had was almost kind of like a pyramid configuration of the grout bags making up the perimeter around the footing. Those basically acted as forms. So those were installed first. And then after the grout bags were in place, we pumped grout into the void underneath the pile cap itself. Then finally, after all that fill material was placed, you can see there's, it might be a little bit tough to make out in this slide, but there's scour countermeasures placed around the bottom perimeter of all those grout bags, and that was going to provide that long-term stability just to make sure that the grout bags themselves weren't undermined if another storm had rolled through. So there's a couple other details that we included based on the varying degrees of the scour. Here there's one condition where there's some pile exposure, so you have a couple of grout bags placed, and then scour countermeasures go around that. It doesn't have that pyramid structure because the height's a little more, a little less of a magnitude. And then the detail on the right shows no pile exposure, so what we did was just line the piers themselves with the Ajax countermeasures. These details, again, a little bit of different conditions. On the left is a condition where there was already existing grout bags installed, so we had to place new grout bags around that material. And again, in that case, we did see like there were previous grout bags placed, but those grout bags aren't there to prevent future scour. They were only there to fill a void. So to prevent that from happening again, we placed the Ajax around. The figure on the right shows one of the other large scoured areas that have the pyramid structure for the grout bags. And you can see it's kind of a parallelogram, the shape of the repairs. We were trying to economize or trying to make sure we were making efficient use of the material. We didn't want the contractor to be out there spending more time and placing more material, slowing their processes down. So we wanted to make sure that we were catering things appropriately. So wherever we could, we were kind of tapering down the heights and narrowing up the width of the repair area. This is a detail of the Ajax. They're a tetrahedral shape when they're placed in the field. They come to a site essentially practically 2D pieces, two separate pieces that come in and they interlock to each other, and then they produce that 3D tetrahedral shape. And then once you form one, they all kind of stack nicely together in a matrix, and then they get placed on the stream bed in that condition. And it really provides a good stability to the overall system itself. The environmental agencies look upon this system pretty favorably because the Ajax do leave little nooks in between their interlocking areas, so that actually promotes some habitat from the fish and the wildlife in the water. This slide just kind of goes over some of the quantities that we were coming up with for the repairs, just to give you an idea on the scale of what we were achieving here. So the scour countermeasures, we were roughly around 100 to 180 square yards of coverage at each pier. And then we have geotextile and stone going down as well. And the grout volume changed rather substantially, anywhere from 30 cubic yards to as many as 360 cubic yards at the worst scoured location. So it was a lot of material that was going in here. So kind of going through construction now a bit. This is the contractor's main barge underneath the bridge. That view was taken from the bridge itself. Here's a view approaching the bridge. They have the grout trucks up on the Tunney Bridge, and that is being pumped down to the workers level down below. This is the staging area for the contractor. A nearby marina was available just east of the bridge. This is where they were putting all their Ajax bundles together. These were wrapped in 2 layers of geotextile based on the field request. This allowed them to reduce the amount of stone that was being placed. Essentially, the 2 layers of geotextile were intended to be redundant. It was likely that one layer was going to rip, so the second layer was there to kind of fill any like little tearing that would happen as the Ajax were going in. Here's a couple of pictures of the tug barges that were used to deliver the Ajax. And here we are at the barge where the contractor developed a little frame to perform the lifts for the Ajax units, and they were able to make use of a pretty small crane as the loads were pretty small to place the units themselves. At all times, there was a diver in the water guiding the material, making sure it was going in at the right location. You can see their snorkel gear a little bit on the left side photo, and on the right, visibility was difficult, especially at the deeper scoured areas, and the material was still very disturbed underwater. So the contractor was spray painting the ends just so it was kind of easier to identify as they were being placed. A couple of the construction challenges that were faced, there were weather fluctuations and work interruption. Shortly after the work started, Tropical Storm Nemo came through the area, and that resulted in quite a few changes in the bay bottom itself because the material was still disturbed and easily moved. So that resulted in even larger areas, larger uneven areas that weren't really anticipated. The contractor worked with this by getting more leveling stone. Number 57 stone was used just to kind of make things workable for the contractor. One thing that was actually encouraging when that happened, some of the countermeasures were already placed, and they performed well. They stayed in place and actually attracted some siltation as a result of that storm kind of blowing through. There was also a request to change the grout mix design that was included in the specs. The grout was really primarily just a fill, so there wasn't too many structural requirements, so we were able to accept that request. So now to kind of quickly go through the current conditions, we have the luxury of being able to look at some of the recent underwater inspection report figures that were provided. So there was an underwater report developed back in 2016. So you can see the very lowest line here is the result of the storm Sandy coming through and the scour that we had just discussed. And the solid line in this view, which is kind of at the footing level, is where the bed is now. So the countermeasures have really invited quite a bit of material deposition a long time. And you can see that trend continue east, and then again at the different profile lines along the structure, it's pretty consistent. So the underwater inspection team did confirm that the countermeasures are performing as desired. And this one shot is from the Tunney Bridge. Similar work was done there, and again the current grades are now much higher than they were after the storm rolled through. So in summary, we did get good performance out of the selected repair type that was developed. One thing I want to point out too, everything was moving very quick, and we actually were able to move with our multidisciplinary effort to get the new repair work done. And we mobilized quickly, and we had a lot of interaction with NJDOT, who was really critical in moving things forward. It was really only after we got the notice that the bridge can remain open for emergency access, it was about a week later that we submitted our contract documents to the NJDOT so that they can go to construction. So that included all the drawings, all the details, quantities and costs, and the project specifications. So that was all done very rapidly. And that's all in thanks to DOT's attention to this project and the coordination with the industry as well. So just to close, again, we'll make the acknowledgements. NJDOT is the owner, WSP is the prime designer, subconsultants were Churchill and ECM for the underwater inspection. The contractor was IEW Construction Group, and materials were provided by Contec for the Ajax and geotextile, and the grout bags were provided by Fabriform.
I recognize over here that there were some issues that you had to worry about, which you didn't mention. One of them was marine borers, and even in the treated piles, the creosote would have migrated out, and I think that the grout kind of took care of that situation in terms of protecting him.
Correct.
What my question is that because you had this grout in there on timber piles, which would presumably adhere to the piles, did you have a concern with a down drag situation?
Very good question. We did look at it, and it was looked at as dead loading, essentially replacing the sand with the grout. It was a very fluid mix, and we ran the numbers, and our geotech folks were quite happy with the results. But that was definitely looked into.
So you had a very firm bottom.
Yes,
Despite the fact that it displacement piles, because of the firm bottom, we didn't think it was going to be any different.
correct. That is correct. That is correct. Good question.
I was going to ask the same question.
Well, we beat you to it. We'll give you the same answer.
Thank you.
Thank you. Thank you, David. Appreciate it.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.